Question 4 is about the de Broglie wavelength. It's got calculations in. Well, I don't want to do the exact calculations, I want you to do them for yourself. So what I'm going to do, instead of doing that, I've got a slightly changed version of question 4 where it's got different numbers in. So when I go through my version of question 4, the method is the same that you're going to use, but the answers I'm going to get will be different. And a couple of bits of the question are a bit different as well. So I haven't changed where it says a negative muon is 207 times more massive than an electron, because that's a fact, can't change. It says calculate the de Broglie wavelength, which actually says the de Broglie, doesn't it, but we pronounce it de Broglie. The de Broglie wavelength of a negative muon travelling at 2.0 times 10 to the 6 metres per second. That's different from the question you're doing, that speed. So what do you know about de Broglie wavelength? Well, that was a thing we did right at the end of term, so it might not have sunk in very well yet, but it's quite a straightforward equation. The equation for de Broglie wavelength is given by lambda equals h over mv. H, of course, is Planck's constant, that we can look up if we don't remember it. M is the mass of the particle, and v is the speed of the particle. Now, do we know the mass of a negative muon? Well, I certainly don't. So what I would need to do, I need to start looking either in the question, and it doesn't take in the question. So next place, looking on the data sheet. And there's my data sheet, and I'm looking for what it tells me the mass of a muon. And I can't find it anywhere. It's not on. So how am I going to get by? Well, the question does tell us that the mass of a muon is 207 times the mass of an electron. So if I can find the mass of an electron, which is here, electron rest mass 9.11 times 10 to the minus 31 kilograms, the question tells me that the mass of a muon is 207 times that. And while we're at it, in case we've forgotten, Planck's constant 6.63 times 10 to the minus 34 joule seconds. So in my equation, de Broglie wavelength, Planck's constant 6.63 times 10 to the minus 34 divided by, and it's always a good idea to put brackets in here to avoid mistakes with your calculator. So the mass of the muon is 207 times the mass of an electron, which was 9.11 times 10 to the minus 31, and that's going to be times the speed, and the speed is 2.0 times 10 to the 6 meters per second. So I need to just extend that little line a bit, make it look better. .76 times 10 to the minus 9. You'll get a different answer because you've got a different speed to work with. Look at the size of that answer. 10 to the minus 9 metres. It's getting on towards the X-ray wavelengths. And that's the sort of wavelengths we'd expect to get when we're talking about particles and de Broglie waves. Second part, and I've actually changed this from the question because yours was about a pi 0. I'm going to do it for a pi minus. It says use the values from the data sheet to calculate the ratio of the rest mass of the pi meson divided by the rest mass of a muon. So, tells us look at the data sheet. Look at the data sheet, and I'm looking for values for the rest mass for the pi meson and for the muon. And the trouble with the data sheet, it doesn't say anything about rest mass, it says rest energy. And that was to be as close as I'm going to get. So if I know the rest energy, can I work out the rest mass? And the answer is that yes, we can, because we know that rest mass and rest energy are related by E equals mc squared. But if we're smart about this, we might realise that we don't need to convert it to rest mass, because the question only asks us for the ratio. Now if we took the rest energy for the meson, and it was in electron volts, so if we convert it to joules, then we use E equals mc squared and convert it into kilograms. And then we did the same with the muon, took the rest energy in megaelectron volts, converted it into joules, used E equals mc squared, converted it into kilograms. If we divided those numbers, all the conversion factors would disappear. And that tells us that if we just want the ratio, we don't have to bother converting. We can just take the rest energy in megaelectron volts for the meson and divide by the rest energy in megaelectron volts for the muon, and the answer we get is just the same as we would have got if we'd converted them both into joules and then into kilograms. So no point doing the conversion, so we just take these numbers that are given, take the rest energy for the pi meson, divide by the rest energy for the muon, and that's going to give the ratio. It's the same as the ratio for the masses. So the values we need for the pi meson, we're doing a pi minus. In this question, you'd actually be doing a pi 0 when you're doing yours. Pi minus is the same as a pi plus, 139.576. And the muon, it doesn't matter if it's a mu minus or a mu plus, 105.659. So to work out the ratio, it's equal to 139.576 divided by 105.659, and get the calculator on that. Get an answer of 1.32. For the last part, we need to think back to the original equation we had. The equation for the de Broglie wavelength, lambda equals h over mv. And the question says, calculate the speed necessary for a pi minus to have the same de Broglie wavelength as the mu minus that we started with. So we'll look at the equation. The de Broglie wavelength depends on m times v. So if we want the de Broglie wavelength for the pi minus to be the same as the one that was in the first part of the question, then m times v's got to be the same for the pi meson as it was for the muon. Now, in the second part of the question, we worked out that the pi meson is heavier. It's got more mass than the muon. The mass is 1.32 times bigger. So if we want m times v to have the same value, if the mass is 1.32 times bigger than the muon mass, the only way we can keep m times v the same is if we make the speed smaller. We've got to make the speed smaller by the same factor. So the speed of the pi meson must be the original speed that the muon had divided by 1.32. So v equals that original value that the muon had, 2.0 times 10 to the 6 divided by 1.32, 1.52 times 10 to the 6. Actually, we'll put 1.5 because there's only two significant figures in the question. 1.5 times 10 to the 6, it's the speed, so it's meters per second.